Okay, good morning, Cisco Cohort 3. This online lecture session is being recorded, and it will be posted and just very shortly later on today after the session ends, it'll appear in the recorded presentations on the left-hand portion here of my TCC Blackboard. Okay, so here's what's on tap for today. Mouse working? Mouse? Oh, I got to go to this tab over here. Okay, there we go. So we're going to cover today, Tuesday, we're going to cover the Module 5 on spanning a tree protocol and Module 6 on EtherChannel. And then Thursday, the in-person lab opportunity, we'll be doing Lab 6.4.2. And let me show you where the PowerPoint presentations are today, because I'm using one that's not that obvious. I'm going to click on Course Presentation Materials. And I'm going to be using this one first. It's called Spanning Tree Protocol from the old Exploration curriculum. It's got really good graphics. I really like it. And then when I finish covering that one, we'll cover the official Module 6 EtherChannel for today. Before I launch into these two, however, let me stop this. Stop this. Hold on. Share this screen. Entire screen. In the news from Cisco Networking Academy this week, the Academy has released a new update, version 8 of Packet Tracer. We've been using version 7.3. It looks just the same. Behind the scenes, there's some new physical hardware features, some rack and stack features that are really cool, particularly when many students are doing remote learning at the Cisco Networking Academy, and they just can't come into the laboratory and get their hands on the equipment. And even you guys that come in person, I can't let you get your grubby grimies on the equipment and manhandle the wires. We have to wait. The chancellor wants to wait until the virus has been, gone out for a while, and then you'll be able to get more hands-on and wire up your own equipment. So this new feature in Packet Tracer is really cool. I'm going to show it to you just a minute or two right now, and then we're going to launch into the death by PowerPoint stuff. Okay, oh good, we're taping, all right. So here I am up at the Packet Tracer. Oh good, my mouse is visible. And normally when we would click on a device and drag it into the curriculum and then click and add the wires and that sort of thing. This is a logical view. It's very much like the front page of the lab reports. They show the logical, but it has no physical. So here is the physical has been in here for a while, but they've done some really great improvements to it now. And it's going to give you more of a feel for what it's really like to drag things out and actually put them in a rack and actually run the wires and connect them together. So what I did is I clicked on physical, and then I'm going to click on this home city, which is the only graphic that appears. And I'm going to go to our office, and then we're going to go into the main wiring closet. And let me reduce this a little bit so we can see what's going on. I'm going to add a rack to that. Make it smaller so we can see the whole thing. And then I'm going to zoom in later, we can see it a little bit better. So normally I would provision some devices to go in the logical topology, and I'm going to do the same sort of thing here. I'm going to click on the network devices, and the first thing we're going to be talking about today is spanning tree protocol, which is a protocol that runs on switches. So I'm going to choose a couple of these and drag them up in the topology. See if I can move that power supply. That's not a top of rack switch. That's a power connection. Okay, I'm going to move these switches a little closer together, and then let me blow this up so we can see them better. And I mean really blow them up. I don't think I'll make them any bigger. Okay, so here we go. So here's our switches in the topology. These are the exact same types of switches that we use in the lab. This is the same switch we use in the 2960 switch. And so here's a new feature that was not in previous versions of Packet Tracer. When you connected the wires, you couldn't really see where the wires were going. They were sort of tucked away. So I'm going to go and The first thing we're going to be talking about is spanning tree protocol, which is a protocol that when our loops are present in the wiring between switches, it can create problems. We're going to see the three big problems there in just a moment. I'm going to go ahead and create a loop. And so I'm going to go and pick up an Ethernet cable. And I'll run it between, well, we've always run it from one of the first switch to one of the second switch. I'm going to delete that. I'm going to change that slightly. I'm going to delete the cable. And I'm going to run it between, so you can see the lay of the cable. I'm going to put between one of the first switch and three of the second switch. And then you can see how that cable sort of lines up there between the two of them. And you can always put your mouse over the cable and it'll show you, it'll change color so you can see which one it is. If you got a bunch of cables in real life, you can't tell which one is which. Notice the two lights have turned orange. This is entirely due to spanning tree protocol. It takes about 30 to 50 seconds and they'll turn green. And while we're waiting for them to turn green, I'm going to add a second cable and create a loop. So I'll pick up another cable and I'll put it in this port here and this port over here. Now notice the two ports on the left of the two switches have turned green by now. In about 50 seconds or so, the link has gone, okay, the two ports on the right-hand side are still orange. So after you connect a cable, or if you do a shutdown command, the do no shutdown command, that delay is for while the STP process is checking out to make sure there's any loops in the topology. If there's any loops, he's got to do something about it. So what is he going to do about this loop we created, which we're going to see in a minute on the slide? This could be a big problem. Okay, so the green light, see, does my mouse show here? The green light at the top of this cable, the light has turned green. But look at the light at the bottom. It's orange, which means it's not in the active state. It's not going to turn green at all, because if it were to turn green, it would create a loop, and the loop could create a dangerous condition. So I really like this new feature in Packet Tracer because you can see the switches up close and personal. You can even see the back of the switch. Well, why do I want to see the back of the switch? Well, maybe I want to plug a console cable into it. Maybe I want to take a PC and plug a console cable into that and do it just like we would do in real life in the labs. So it's very much improved graphics capabilities in this rack and stack feature. And just to show you, I'll just take one more minute and show you another cool thing you do. Let's reduce this down to the demo size. So here's our two switches. And I'm going to go ahead and add a desk or a table. Let me move the switches down where they're closer to the side of the desk. So if I wanted to add, say, a PC to this, I'll add PC A, I'll add PC B. We blow those up a little bit where they're a little bit easier to see. And if I wanted to, say, connect PC B's, I want to connect PC A's serial port to the console port of the rear of the switch. I could very easily do this. So what I'm going to do is I'm going to click on this. Oh, sorry. I want to get the rear of it. There's the rear of it. So I'll select the navy blue console cable, plug it to the console port, and plug that into the RC32 port on the PC. And there, it's plugged in. Just like in real life. Just like in the real labs. When you come in and do the real labs, each one of your PCs has got two console cables, and each one of your PCs has got two Ethernet cables. If I wanted to plug the Ethernet connection of this PC A, configure with IP address, I click on the Ethernet cable, click on the fast Ethernet port, and I can plug that into a port of one of the switches. And just like that, you can see the layout of the wires. Now, if you want to clean up the wires and tuck them away where they don't look nice, you can say manage all the cables on the rack, and it kind of hides them and tucks them away. But I like them to be out there in the open where you can see where they're lying around. Pretty cool feature in the new Packet Tracer. Okay, so I'm going to stop sharing that. And it's time to start sharing PowerPoint slideshow. So share file, and we'll start the first one. I'm so sorry, I forgot to turn the mic back on. Okay, so let me start again. We want redundancy at the distribution and core layers. So we have multiple switches here. So I've got a triangle connection between all these three switches. So if any one of these wires failed, there would be another method to connect. We'd have multiple switches, multiple trunk links. If any one link fails, some other device can take over. But the problem is redundancy creates loops. So switching loops, if all the links are active, here's the three big problems. We're going to look at all these and see why this occurs. So switching loops gives us a problem if all the links are active, because we can have, well, first of all, we can have broadcast storms. We can have multiple frame transmissions where we have more than one copy of a frame being received by the destination workstation, and we can have inconsistent switch tables. So let's look at the first problem. Let's say this workstation over here on the left sends an ARP request. Now, ARP request is a broadcast. Our two biggest sources of broadcasts in any Ethernet network are ARP requests, which is, this is calling all stations. If your IP address is 192.168.1.1, please send me back a reply, an ARP reply, telling me what your MAC address is, because I need to transfer some data to you. I know your IP address, but I don't know your MAC address. Workstations only hold on to MAC addresses in the ARP table for about 3 or 4 minutes. So if it's been more than that amount of time, the workstation will have erased it. He will have forgotten it. So he needs to ask for it again. Or the first time in the morning, he needs to ask for it the first time. So he sends the ARP request, which is in the form of a broadcast. So this broadcast goes into the switch, goes into this directly connected to the switch right here. Now, what are Ethernet switches compelled to do whenever they receive a broadcast? They're compelled to send that broadcast out all the other ports that are active. So he's going to flood the broadcast through all the other ports, not the one it came in on, not the source port it came in on, that port 3, on that switch in the 9 o'clock position. He'll send it out all the other ports. So here we have 4 switches connected together for redundancy. We have some, if any one of these wires fails, we would still have a connection. And so the broadcast is flooded up to the switch at the 12 o'clock position. And then he floods it back to the switch at the 3 o'clock position. And then he floods it back to the switch at the 6 o'clock position. And then he floods it back. And all of a sudden we have a situation here where we have a bunch of excessive copies of this first original ARP request is being flooded throughout the network, and nothing can stop it. And pretty soon, it's consuming so much bandwidth and processing power on these 4 switches that no more legitimate desired traffic can pass. So that's called a broadcast storm. That's a big problem. We don't want that. Another problem is, let's say A is trying to send something to B. B's over on the right-hand side of the screen. So this is an unknown unicast. The B workstation is not in the MAC address table for the switch over the 9 o'clock position because it's not connected to that switch. So another thing that causes switches to flood frames is if they receive a destination Ethernet frame. Okay, now he's already done this ARP request. He's already learned B's MAC address. This is not a broadcast request. This is a unicast frame from host A to host B. So the first switch at the 9 o'clock position receives A's unicast transmission to B. It's not in the MAC address table. So when switches encounter a destination address they don't know about, it's not in their MAC address table, they flood it just like if it was a broadcast. So it gets flooded to the switch at the top at 12 o'clock position, the switch at the bottom at 6 o'clock position. And so they both flood it to the switch at the 3 o'clock position. And host B receives 2 copies of the frame. The frame arrives and the frame arrives again. Now, depending on how well the people wrote the lines of code of whatever program this is running on the machine, it could confuse him and he could crash. If it's Windows, he's going to crash. Who knows? Windows, it's not that great with operating system. If it's Linux or Mac OS, it's probably going to survive it and not crash. So extra copies arriving when he only needed 1. And another problem is A sends a frame to B. So it gets sent out the switch at the 9 o'clock position, and it goes down to the switches at the top 12 o'clock position and the bottom 6 o'clock position, and sort of more get reflected in a loop block before. and the switch MAC address tables are inconsistent. Is A is really on port 3 of that switch in the 9 o'clock position. But due to the reflections he's got back from the other switches, he thinks, only one device is allowed to have one MAC address. Now it looks like I have 3 devices switch at the 9 o'clock position. It says, I have devices plugged into ports 1, 2, and 3. They're all the same MAC address. That's not possible. That's inconsistent. So those are the 3 big problems. Now, even if you didn't set up a deliberate loop for redundancy purposes, like I just did in Packet Tracer, I set up a deliberate loop just to show you how when STP is on, he did not light up 4 green lights. He only lit up 3 green lights, and he partitioned one of them away so a loop would not be created. It's possible to create loops by mistake. These wiring closets can be pretty complicated. Here we've got a 48-port patch panel, a bunch of switch patch cables going between the switches, and the connections going to the various offices and cubes. So you could accidentally create a loop by mistake. Okay, there is an exception, and we're going to get this in the second presentation for today, something called EtherChannel. If I want to increase the bandwidth between S3 and S1, let's say I'm running fiber optic cables and S3 is here in the engineering, in the South Campus Business SBUS building, Computer Science building, and S1 is in the academic computing, classroom building next door where the big distribution layer switch we connect to is. And if I ran one piece of fiber optic cable, I could only get maybe 10 gigabits. If I run 2 pieces of fiber optic cable, I could get 20 gigabits of throughput. Gosh, we got 400 or 500 computers here in the upstairs and downstairs in the computer science and accounting department. We need a little bit more bandwidth than just one fiber optic cable. But STP would partition one of those off because they create a loop. A loop is created between S3 and S1, just like I did in the Packet Tracer illustration. So we're allowed to logically combine. Remember when we did VLAN, inter-VLAN routing, we logically split a physical Ethernet port into multiple sub-interfaces, VLANs 10, 20, 30, and unwanted. And this is kind of the same way except on steroids. We're logically combining 2 physical Ethernet ports and telling the switch to regard them as one wire. So once they're bonded together using EtherChannel, and we'll see that in the next chapter, which we're going to cover today, they'll act as one link. It'll be like a super fast wire that's a pseudo wire that's 20 gig of bandwidth instead of 10 gigabits of bandwidth. So when we do this, EtherChannel will not turn them off. Okay, so there needs to be just one path. But we want redundant paths. In case the main path gets dug up by the water crew and they dig, the number one enemy of fiber optic cable is backhoes. They dig a ditch and they cut it back, and they cut a fiber cable. But if a redundant path has been laid, well, it'll do this. It'll start using this instead. So spanning tree protocol works in the background. We don't have to sit there and wait for people to cut cables or accidentally create loops or move wires when they shouldn't have. It will automatically create a loop-free topology, and if something changes, he'll very quickly recover from it. So what the heck is a spanning tree? It's a tree topology, an extended star topology. No loops. All devices are connected. Well, this is not a spanning tree. It has loops. It has too much redundancy. Maybe we physically wire it this way so that if one fiber optic cable goes bad or a port goes bad, it could start using another one as a backup. But as it is right now, this has loops. So it would create broadcast storms and other problems that loops create. Now this is a spanning tree. There's no loops, but one of the devices is left out. It's not connected. It doesn't span all devices. That's better. Now we've got a spanning tree, which logically has no loops. All devices are included. We can actually run more physical wires and create redundant topology, but spanning tree will sort of electronically, mysteriously disconnect them so that they won't create any loops. It'll do that for us automatically. So we're going to use the spanning tree protocol, which, by the way, is built into all Cisco switches and most other manufacturer switches. It's automatically activated. You don't need to turn it on. So it's used by switches to turn this redundant topology into a spanning tree. It's going to disable the links that would create broadcast storms and create a loop by blocking certain ports. Now, this is an IEEE specification. 802.1d is the specification for our standard spanning tree protocol, which is owned by default on all our Cisco switches. the rapid spanning tree protocol, which converges a little more quickly. It doesn't take almost a whole minute. It took us almost a whole minute, about 50 seconds, before that orange lamp turned green when we connected the two Cisco switches together. So it has its own specification. You know, engineers and academic people just love to sit down at the table and create specifications and argue about it. So switches run STP by default, no configuration required, and it'll just work all by itself. So here's the spanning tree algorithm. We're going to choose one switch to be the boss switch. We're going to call it the root bridge. Now, switches used to be called bridges. As a matter of fact, the same lady, Radia Perlman, who invented the first Ethernet bridge, also invented spanning tree protocol. And she did this over the weekend, one weekend. Pretty smart lady. We're going to choose one switch to be the root bridge using some Elven magic we'll see in a moment. Then on every other switch, we're going to choose a root port, which is the fastest path, the bestest path, back to our root bridge. Then we're going to choose a designated port on the other side of each wire, and all the other ports, they're going to be closed down. Yeah, otherwise, it would create a loop. So let's look at this process here. Somehow, for some reason, we don't know how yet, we see how, we have determined a root bridge. I'll give you a sneak advance peek here. It's going to be mostly based upon what the MAC address of that switch happens to be. So the root bridge is the one at the top at about the 12 o'clock position here. The two other B and C that are connected to it, most directly connected to it, each one of those is going to choose the one port on, B is going to choose the one port he has that's most closely connected to the root bridge, and in case it's this one right here. Because he could go through this one, but it would be a double bandwidth loss. The C switch is going to choose his one best connection this way. Otherwise, if we went the other way, it would not be a more optimum path. Now, our little isolated switch down here, what's his best pathway to get back to the root? Well, if it goes through B and then straight to A, that's the best path. Fewest number of hops. If he went the other way through switch C, it would be a longer path. So our one point here where a loop could be created is this point right here where the red X is. We're going to, now he says close down. That implies you type the shutdown command. No, it's not shutdown. It's waiting, it's listening to all traffic, because if it needs to take over, if some other wire went bad, it would need to take over and still be used. So how do we choose the root bridge? Well, what we're going to do is look at the MAC address, the built-in, burned-in master MAC address of each switch. And each switch has, by default, has something called the bridge ID. It's a priority value, which by default is, if you take 2 to the power 16, it's right in the middle. So switches exchange bridge protocol data units with each other, in which they advertise what their bridge ID is, what their MAC address is, what their default priority value is. You're allowed to change that if you want to rig the election. The switch with the lowest bridge ID becomes the root bridge. So administrators can fix the election. You probably don't want a little $500 Cisco 2960 access layer switch to be the root bridge for your whole company. You would probably rather it be, oh, $1 million Cisco 6500 switch with super high power processing capability. An analogy would be in Microsoft networks. We designate a master server to be the domain controller, and the backup domain controllers. For our Microsoft network, when people log into the network, they put their passwords in, the domain controllers check their passwords and give them access to the network. You probably wouldn't want to use a sub $1,000 junky Dell workstation to be the domain controller for your entire Microsoft network. You probably want to use a $50,000 high-powered rack mount server with RAID driver arrays and 16 CPUs and lots of memory to do that stuff, because it requires a lot of processing power. So the bridge ID is composed of the bridge priority value. By default, it's 32,768. That's exactly halfway between, let's see, If we have a 60, it's a 16-bit value. So 2 to the power 16 is 65,536. It's halfway between that and 0. Lowest priority wins. The extended system ID is used to allow for VLANs, because every VLAN is a separate broadcast domain. That means if we're running 4 VLANs, we have 4 copies of STP running. So the MAC address is going to be used if the priority is the same. So you can take completely unconfigured switches, factory fresh from Cisco, plug them all together. Automatically, a root bridge will be chosen. Automatically, all loops will be eliminated. Automatically, we're going to get fairly decent performance. But in a large environment where we have cheaper access switches to connect to our students or to our employees, and more expensive distribution or core layer switches to connect all the buildings together, we probably don't want the cheap access switch to do it. We probably want to rig the election ourselves and make the more expensive switch of a higher processing power. If it doesn't happen the lowest MAC address, we're going to configure it so that takes place. So here's a command to set the priority. I don't like this one. Oh, how are you going to remember? Oh, I'm taking the Cisco test. What was that number? 24,576. So I like this one. Whatever one is my fast switch at the center of my topology, I want it to be the root because it's got the fastest CPU, the most memory, the best processing power. I'm going to say spanning tree, VLAN 1, root primary. And then the one I don't want to be the primary and the secondary, I'll set it to be secondary. So if the primary root bridge fails, primary switch fails, the backup switch will take over. So let's choose the root bridge. So we're going to start a series of switches up there, plugged together. They're all going to start sending out bridge protocol data units back and forth to each other. And at first, each switch says, oh, I am root, all hail me, I'm the boss. I'm at the top of the mountain. Until all the other switches receive a bridge protocol data unit with a lower bridge ID, they say, oh, I guess I don't get to be the boss. I'm going to defer to the switch that actually had the lowest MAC address, or the one that the network engineer manually configured to have a more attractive priority value. And that will become the root bridge. So eventually, within a few seconds, all the switches agree with each other that the switch that happened to have the lowest MAC address or the lowest priority value will become the root bridge. And that's the central reference point for our entire network. So here we have our similar diagram. Let's just say that the system administrator, the network engineer technician, has manually configured this bridge, this switch A, to be the root bridge. Maybe it's back in a wiring closet and it's a more powerful system than the edge switches that are connected to our devices. So every switch that's not a root bridge, in this case B, C, and D, they need to select the best path back to the root. That's the lowest cost path back to the root bridge. And they're going to choose that based upon how fast is that Ethernet connection between them. So for example, if it's a gigabit Ethernet connection, it's a more attractive path than maybe a fast Ethernet connection. So this cost is based upon the speed. Now, before the days of gigabit Ethernet, 100 gigabit Ethernet, they didn't anticipate the speed would be so fast, so they revised them. So standard old fast Ethernet, our Ethernet switches that we have at 24 fast Ethernet ports, the cost is 19. It's a inverse relationship, like a fraction. The gigabit ports have a cost of 4. Lower is better. The lowest one, lowest MAC address, lowest cost. We're going to pick the lowest value here. This is what we call a metric. I can manually change the cost of the link. Now at the CCNA level, there's no good reason to do this. Maybe if you're using a mixture of Cisco devices and other vendors' devices, you might have some reason to do this. This is really sort of a CCNP type of a topic. So this is sort of, know that this command exists, but you probably won't need to use it. So I would type spanning tree cost to change it. If I wanted to put it back to the default, I'd say no spanning tree cost, and it would erase it and go back to the default. Now, what if all ports have the same cost? We have 4 of our cheap $500 Cisco 2960 switches connected together using the standard fast Ethernet ports. So by default, every port has the exact same cost, 19. Which, now of course, A is the root bridge. Of course, B is going to choose this root port to go back to A. Of course, C is going to choose this root port to go back to A. But what is D going to choose? He has two equal cost. 19 plus 19. The cost is 38 this way. 19 plus 19. The cost is 38 this way. It's a tie. Which one do I choose? Well, they're going to use the port priority value. So in this case, port number 1, port number 2, the lower numbered port will win. The lower numbered port will become the designated port, and the higher numbered port will become the port that's blocked by default. I can configure this by hand. If I don't like the number, the physical number that was actually on that switch, I can configure the desired copper cable or fiber optic cable to have the higher priority. So by default, the priority is 128. The lower port priority value wins. So the losing port is, this is not exactly accurate. It's not shut down. It's in a sort of a limbo state where it's listening. It's just not active on the network because it needs to listen to the traffic to determine that the other port, the designated port, is still working. If he stops working for some reason, like if the fiber gets turned up, he needs to come over. The port that was temporarily blocked needs to unblock himself and start being used so we can get the redundancy that we needed. So every bridge protocol data unit, which is sent out by the root bridge every 2 seconds, includes the cost of the path back to the root bridge. The cost is the total cost. So in that last diagram, it was 19 plus 19. The total cost was 38 from the bottom switch to the top switch. So as every switch receives a bridge protocol data unit, he just adds his cost and passes it on to his neighbor. So the port with the lowest cost becomes a designated port. So here we have switches B and switch C. They've determined the root port, the lowest cost, back to the root bridge. And on this wire between B and C, they'll choose which one based on the port number. So designated port, if it's the same cost, it will become that. All the other links in this case, this link here coming out of port C, going back to port D, is in the blocking state. That's not shut down. It's red. It looks like it's shut down. It's not shut down. It's active. It's not active. It's passively listening to all traffic so that if something happened to switch B, he would be able to take over and continue the traffic. For example, it may be this wire got dug up by the backhoe. Well, now it's crucial that he stop becoming X and start working again as a backup path. And that will happen very quickly within a few seconds. So the bridge protocol data unit information is put in an Ethernet frame. These are Ethernet switches. They send Ethernet frames back and forth to each other. So there's a special multicast address, which is designated for spanning tree activities. Remember that multicasting was our way of sending to a group of devices, in this case, a group of switches. And so port roles, spanning tree protocol is going to make ports in one of 3 states eventually. Root ports are going to forward data. They're going to actively forward data back and forth. Designated ports are going to forward data back and forth. Non-designated ports, and I don't like the word shutdown, they're going to be inactively, so far as forwarding data is concerned, but they're going to keep actively listening to the traffic to know that they should take over in case one of the other root ports or designated port stops working. They need to be a backup and start working. So here's this 50-second delay. I plugged in the wire and the link light turned orange for about 50 seconds. Here's what's happening. In the first state, which lasts for about 20 seconds, the port is in the blocking state. He's receiving and transmitting bridge protocol data units from the other switches because he needs to learn their MAC addresses in case he has the lowest one, he wants to become the root. Then he goes to the listening state for about 15 seconds. He continues to receive and transmit bridge protocol data units from the other switches. Then he goes into the last state for about 15 seconds of learning. He continues to receive and transmit bridge protocol data units and starts learning the MAC addresses in endpoints in systems like desktop PCs and printers. And finally, he's going to go to one of two states. At the bottom, he's either going to forward or be disabled or blocked. If he was not going to create a loop, if this particular connection is not going to create a loop, he will go into the forwarding state. The light will go from orange to green. And that took about 50 seconds. Let's see, I only went to public school, but it's 20 plus 15 plus 15 is about 50 seconds. If it had determined, if the switches had determined between themselves that this would create a loop, then that port will be, it is not administratively shut down. That is wrong. It is blocking. It's waiting in the background and listening to everything. So it's not administratively shut down. It's just blocking. So blocking state for 20 seconds, listening state for 15 seconds, learning state, and then forwarding state. If it would create a loop, it's going to block and stay blocked. No traffic will be passed. Bridge protocol data unit timers optimized for a 7-switch diameter network. So that way the network has time to converge and decide who's the root and fix all the loops that might exist before forwarding data. So this is not at the CCNA level. We better not mess with these timers. There are commands to adjust these, but we shouldn't do this. If I change the command spanning tree VLAN 1 root primary diameter 5, I shouldn't be doing that. I'm just a CCNA. I better leave that to the CCNA or CCIE engineers to determine if that's necessary. Out of the box, they're going to work just fine, optimized for a 7-switch diameter. We normally don't need to change those. Okay, now I'll tell you a story. I used to run a Novell NetWare PC local area network based network. So back from about 1980 to about 1995, Microsoft really didn't push their Microsoft server business and their networking business. They didn't really pay attention to this internet stuff. So Novell Network in Orem, Utah had the greater share of market of servers. You'd buy, Windows Intel a box that could run Windows, but instead of installing Windows on it, you would install Novell Network. And Novell Network would boot up very quickly. In about 1995, Microsoft started pushing Windows Server as a competition for this, and all the marketing people said, "Oh, we need to switch to Microsoft." That's what my company did. They said in 1995, "We need to get rid of Novell Network and get Microsoft Server because Microsoft is so big and they're going to give us a better deal." So now, of course, these days Windows 10 takes a couple minutes to boot up on a high-powered workstation, but in those days we were running older versions of DOS, even non-Windows versions, and they might boot up in 10 seconds. So the secretaries running the word processing software, their workstation could boot up in like 10 seconds. And the 50 seconds had not yet elapsed. And so when they tried to log into the Novell Network server so they could start working on their word processing document and send it to the laser printer, they would get a timeout error. If they just wait, of course, they would call the help desk immediately. Timeout error, come fix it immediately. And the help desk would say, press Control-Alt and delete on the keyboard. The machine will boot again. And by this time, the 50 seconds at the switch would have elapsed. They could log right in. But it annoyed the word processing clerks. So thinking about when we connect switches to other switches, we would normally connect a switch to another switch and make that a trunking cable. If we connect a access port from an access switch to a secretary's PC, that's normally not going to be trunking. It's going to be just a regular old Ethernet port. So that wire that goes between, say, port 6 of switch 1 to a workstation will never be connected to another switch and never could possibly create a loop. So we have a port fast command that allows us to speed up this 50-second interval to 1 to 2 seconds. And just in case some technician accidentally moves that port and connects it to another switch, it'll go through the whole 50-second thing again. But if it's how does it know it's not being connected? How does a switch know it's being connected to another switch and not connected to a Windows workstation? Well, Windows workstations don't send and receive bridge protocol data units every 2 seconds, but switches do. So if a switch port hears bridge protocol data units coming into this port, he knows, by gosh, I'm connected to another switch. And we need to check and see if this wiring segment needs to be looped or not. So this speeds up the access to the users. And this took care of the problem with when I worked for a company in the 90s and we connected Cisco 24-port switches. It was still running double network. I would always configure all the ports that went to the secretaries to be port fast so they wouldn't complain about this. Now here's a command that we can verify what's going on with the spanning tree. In this case, we've gone to a switch and we type the command show spanning tree. You can type show span for short. And it tells us what the priority is of the root bridge and what the priority is of this switch. So we can tell, there's two ways to tell whether when you type this command show span on a switch console port, if this is the root bridge or this is not the root bridge. The first one it says is if the root bridge and this switch reports are different MAC addresses, you know you are not the root bridge. If you were the root bridge, where it has this arrow that says this switch, it would have a line that says this switch is the root. This bridge is the root. It'll tell you. Another way you can tell is at the very bottom. You won't have, if root bridges don't have root ports. That's kind of weird. Root ports only exist on all of the other switches. They're one best path back to the root bridge. So if you show span and any of those interfaces have the word root, this is not the root bridge. It's one of the other bridges. So that's two ways you can tell that. Now, this is kind of technical here. If a topology change occurs, say a fiber optic cable is dug up by a backhoe, or some technician adds a new piece of fiber optic cable. If there's a topology change, they need to know. So the switches generate something called a topology change notification, and they send it so the root bridge knows. And if they need to reconverge. They might need to change into a new root bridge or disable a new port, a new loop that's been created. Now, in spanning tree developments, all of our switches use something called Per-VLAN spanning tree protocol, PVST. There's a separate copy of spanning tree for each broadcast domain, for each VLAN you create. Because the problem, spanning tree prevents broadcast storms. Well, if we have two VLANs, we have two broadcast areas. They could each have their own broadcast storms. There's another Cisco proprietary method that supports the IEEE 802.1q standard, Per-VLAN spanning protocol plus, and then rapid spanning tree protocol, which cuts that 50 seconds down to a couple of seconds. The IEEE guys have come up with their own standards, just like they came up with their own version of Ethernet frames, and it's called rapid spanning tree protocol or multiple spanning tree protocol. So let's take another closer look at this Per-VLAN thing. So here we have a network that would set up two VLANs, VLAN 10 and VLAN 20. Those dotted lines connecting the three switches together, those represent trunking connections. We've configured all those connecting ports to be switch port mode trunk, and the trunking wires carrying all the VLANs in them, and these tagging the VLAN 10 and the VLAN 20 with the VLAN ID 10 and 20. It is possible to have one root bridge for one VLAN on one switch and one root bridge for a second VLAN on another switch. If it's a small company and these are just $500 Cisco 2960 switches, this is a way to spread out the load. So one of the $500 switches doesn't get overwhelmed. In this case, S3 is the root for one VLAN and S1 is the root for another VLAN, and that reduces the load on them. So that's a good thing that they come up with. Per-VLAN spanning tree protocol plus is the default configuration for our Cisco 2960 switches. So the VLAN needs to be identified. Each of the bridge IDs that are sent by the bridge protocol data units has got the priority, the extended system ID field, which is simply the number of the VLAN, and the MAC address. Originally, when Radia Perlman first invented this, it just had the priority and the MAC address because there was no such thing as VLANs yet, back in the early 90s when she came up with this. But when they came up with VLANs, they had to come up with this, so they had to take this priority value, the 16-bit priority value, and they had to chop it up into smaller pieces. We need 12 bits now for the VLAN ID, could be to the power 12 or 4,000 VLANs. So now we just have a 4-bit value for the priority. That's why it has to be multiples of 4,096. Yeah, nothing confusing about that. Okay, rapid spanning tree protocol, it's compatible with it. Much faster conversions time. Same structure, except it just puts number 2 in the version field, still sends the bridge protocol data units every 2 seconds. The roles and states, we gave them different names. They do pretty much the same thing. So an edge port is like port fast. An edge port is a port that will never connect to another switch. It immediately goes to the forwarding state. Well, it takes about 1 second. It's the same thing as Cisco port fast. So I'm going to use the same exact command. I'm going to go to that port. I'm going to say spanning tree port fast. Now, when I configured all 24 ports of these switches back in the 90s to go to all the secretary's workstations, I would do interface range FA01-24, spanning tree port fast. I'll do all of them. He puts a warning on the screen when you do that, because if you connect this to another switch, you could create storms. He warned you. Now, if I lie to the switch and create an edge port, and I say, this is an edge port, it's only going to an employee's desktop PC, but then plug it into the switch anyway, if he knows, because he now hears bridge protocol data units, which only switches in between switches. And he says, you liar. And he converts it back to a normal spanning tree for me. So it's very hard to sabotage the network. Now, a link operating a full duplex between 2 switches is point-to-point link. This is the only thing we use today. We don't use half duplex hubs anymore. Links operating in half duplex is shared link. Who's going to use hubs? The only thing we use hubs these days for is security research, and maybe we're setting up a Microsoft domain controller. You're supposed to plug into a hub, standalone hub, before you plug it into your real network. So ports on a point-to-point link, they're able to move to a forwarding state quickly. So in the rapid spanning tree protocol, this takes place very quickly. So remember, in our old STP, it was blocking, it was listening, it was learning, and then it was forwarding. Or if it was creating a loop, it would be disabled or blocked. In rapid spanning tree protocol, they just change the names. It still does the same sort of thing, but instead of it being 50 seconds to go through here, it goes zip in about 1 second and very rapidly starts forwarding data. So the secretaries don't get mad with their new laptop PCs that can boot up in 2 seconds. So the root and designated ports, they're just as they were before. The root port is the one best path back to the root bridge. The designated port is the other side of the wire. So here's a one wire. This cable between B and A. The root port is on the bottom side of the wire. The designated port is on the top side of the wire. Root bridges don't have root ports. They only have designated ports. All the other bridges have root ports and blocking ports. So if I have wired, let's say I have this wiring scheme here and I've run 2 cables between 2 switches, and we haven't used EtherChannel yet. They're not bonded together and being treated as one channel. One of them is going to be active and the other one's going to be shut down. By default, the one with the higher port number will be shut down. But it's ready as a backup. It's ready to take over if the root port fails. So let's look at this last slide, and then we're going to go into EtherChannel. The root bridge should be the most powerful switch in the center of the network. We're going to minimize the number of ports that need to be shut down by spanning tree protocol. VTP is no longer a CCNA objective. Don't worry about VTP. We'll use layer 3 switches in the core and keep spanning tree protocol running even if no ports need to be shut down. What if someone comes into the wiring closet and accidentally creates a loop? They meant to hook up the new dean's computer, but they accidentally created a loop. Oh no, that's terrible. Okay, hang loose 1 second, and I'm going to do the EtherChannel. Okay, so EtherChannel is a method of bonding channels together, aggregating channels together, so that we can double our bandwidth or triple or quadruple our bandwidth. We need more bandwidth, or we need redundancy between devices. A single link is not fast enough. However, if I connect multiple links between switches, and it's usually fiber optic cable because it's usually faster than copper cable, and we want to go like between here and the library, which is more than 328 feet. So spanning tree protocol, by default, it would block the second copper. It would block the second fiber optic cable or the second copper cable, and we wouldn't get the doubling of speed. So Now, Cisco is not the only vendor that supports this. They have their own proprietary method of doing it, and they call theirs EtherChannel, and it's called link aggregation generically among all vendors. So EtherChannel is Cisco's implementation of link aggregation technology that'll group multiple physical Ethernet links together into one single logical link. So this gives us fault tolerance. The cable can be cut, and we'll still get the other cables that are remaining. We can load share among all the wires that are working, increase bandwidth. So if I have 4 10 gig fiber optic cables, I get 40 gigabit. And this gives us some redundancy. So originally developed by Cisco, a local area network switch-to-switch technique. So we have a, let me see, I think I have to turn the pencil again. So here's our access layer switch, okay, serving the classroom computers or the employee computers. And then this is our little icon of a more powerful, maybe distribution or core layer switch. It's a layer 3 technology. I don't like that term. Layer 2 devices are bridges and switches. Layer 3 devices are routers. So what they call layer 3 switches now, the marketing guys came up with, they're not technicians, they don't understand this. So what they call a layer 3 switch or multi-layer switch is a big chassis that has, you can plug in a blade, a printed circuit board that has 24 or 48 Ethernet ports in it, and you can plug in another blade or printed circuit board that has a router on it. And they're all in one chassis, kind of like rack mount servers, where they can have very fast communication and very fast processing. So our little 2960 Ethernet, 24-port Ethernet, oh, $500 maybe. If it's a 48-port switch and has power over Ethernet, it's more like $2,000. These switches run from $50,000 to $1 million. They're much more powerful. So we're going to create these 2 wires going between our switch and the upper switch on the left. We're going to combine those into an ether channel. We're going to double that bandwidth. And let's assume that these dark black cables going up to each one of these 2 layer 3 switches are 10 gig fiber cable. I'm going to get 10 plus 10. I'm going to get 20 gig here and 20 gig here to my other devices. We're going to call that a special interface called a port channel. So here's some advantages. We can bundle 2. I think in the lab you're going to bundle 2 wires together as an ether channel. We're going to bundle 2 wires together and treat them as one physical interface. We use existing switch ports. I don't need to upgrade the link. If I need board bandwidth, I don't need to add a new thing to a chassis and pay for it. If 2 wires are on the same ether channel, there's a sort of load balancing that takes place. It's not true load balancing like a routing protocol would do, but it sort of shares information among both of them. So if you have 500 people in the building, it's going to pretty much average out. 250 people will get one, 250 people will get the other. Now there are, we create an ether channel aggregation, seen as one logical link. If I have several ether channel bundles between 2 switches, STP may block one of them. It blocks the entire ether channel. If I have only one ether channel link, which is the most common, we can put from 2 to 8 wires from one switch to another switch, and they'll become one physical ether channel. And this gives us redundancy because it looks like one logical connection. I can lose as many links as there are in the physical link, except one, and it'll still keep working. It'll just get slower and slower as they get dug up by the backhoes. Okay, here's the downside. There are some restrictions. Interface types can't be mixed. Both of them have to be fast Ethernet. Both of them have to be gigabit Ethernet, or both have to be copper, or both have to be fiber. So up to 8 ports. So I could take 8 fast Ethernet channels and get 8 gigabit. Or I could take 8 gigabit ports and get 8 gigabits. If I had 8 10 gigabit channels, 10 gigabit ports, I'd have 80 gigabit between one switch and another switch. So on our switches we have in the lab, the one we use in the packet tracer has 24 fast Ethernet ports and 2 gigabit ports. I could not combine the gigabit port and the fast Ethernet port together and make them a channel. I could combine 8 of the fast Ethernet ports together and get 800 megabit fast Ethernet channel, gigabit channel, fast Ethernet channel, or I could combine the 2 gigabit ports. You're going to get 2 gigabits, but I couldn't mix and match between them. And our switches have a feature that you can plug in an adapter and use fiber optic cable, or you can use the copper twisted pair RJ45. Have to be on those 2 gigabit channels. It would have to be, both of them would have to be fiber, or both of them would have to be copper. I couldn't use one fiber, one copper and mix them together. Can't do that, even though the same speed. Have to be the same speed, have to be the same wiring technology. Now, remember when we had will it float, will it sync? When you plug 2 Ethernet switches together, will they form a trunk or will they not form a trunk? And we had dynamic desirable and dynamic auto. And so if you went to the switch, first switch is connected to the second switch through both their #1 ports. If I do switchboard mode trunk on switch 1, switchboard, I don't have to type switchboard mode trunk on the second switch. It'll automatically trunk up with the first one because of the dynamic trunking protocol, DTP. So this is a very similar thing. If I configure a port channel on one switch, should the other switch with the other 8 wires on it, should it go ahead and port up or not? So link aggregation protocol and port aggregation protocols are much equivalent of will it trunk, dynamic desirable, and dynamic auto. So PAGP is Cisco Proprietary. If I configure the link using PAGP, PAGP, they're sent between the 2 different switches, and they might automate the forming of an Ether channel. So again, all the ports have to be the same speed, same duplex setting, same VLAN information, otherwise they won't trunk up or form with each other. And normally when you configure 2 to 8 wires together into an Ether channel, you use it as a trunking cable, not an access device. Maybe an access device is to go into a high-powered server. So I can make this mode on, desirable, or auto. Doesn't that sound like desirable or auto for VTP? Yeah. DTP, dynamic trunking protocol, they have to be the same. They have to be compatible on each way. Now, I share a similar philosophy that I did with dynamic trunking protocol. I don't like it. I don't want to use it. I'm going to make switchboard mode trunk and unconditionally make it a trunking port. And when I do PAGP, when I do Ether channel, I'm going to say mode on. I don't want no stinking auto configuration protocol working on there. I wish to be in command. I'm going to type this on both switches and make them become that way. Now, in the lab, they're going to have you experiment with this and use PAGP. It is actually an objective on the test. So similar to the chart we had before with trunking it up between the 2 of them, if I say mode on, I do get an Ether channel. On and desirable, I do not get an Ether channel. Desirable and desirable, I do. Desirable and auto, I do. Auto and desirable, I do. Auto and auto, I don't. Well, that's kind of strange. That's something to hang your hat on, because our dynamic trunking protocol, DTP, auto and auto will not trunk up. Yeah, that's kind of weird. Auto and desirable will. It's almost the same logic. So LACP is open standard. All the switch manufacturers support this. So I can say on, don't use PAGP, don't use LACP. Do it autumn, do it, I manually specified it. That's my preference, my personal preference in the field in real devices. And you can say LACP active or LACP passive instead of PAGP, like you did in the previous command. So you get the same similar combinations of them. This is open standard. So if switch 1 was a real Cisco switch, and switch 2 was a Hewlett-Packard switch or some other brand of switch, you could set up Ether channel link aggregations between them. Okay, let's look at some configuration commands. So Ether channel support, all Ethernet interfaces, they must support Ether channel. Some of the older switches would not support it. I think Cisco requirement is it has to be at least a fast Ethernet speed. So if I had an older Cisco switch that had the standard Ethernet ports, can't Ether channel those together. Has to be at least 100 megabit. The speed and duplex got to be the same. Okay, so I can't mix a gig port and a fast Ethernet port. Got to both be full duplex or for some unknown reason, half duplex. Why would we want that? But it has to be duplex, has to be the same. The VLANs must match, or it has to be configured as a trunk. We're going to configure it as a trunk. Anytime you connect two switches together, you want it to be a trunking connection. The range of VLANs must be the same. If the allowed range is not the same, they will not form up. So just allow them all. So here's a configuration that would form between switch 1 and switch 2. The ports are both gigabit speed. They're both full duplex, and it's VLAN 10. They will form an ether channel. It could be, now the example here, they're VLAN 10, access mode. Not very common between switches. Normally you want switches to be in the trunking mode. That's the most common. Okay, so here's some configuration. I'm going to go to the switch. I'm going to say, I want ports 1 and 2, fast Ethernet ports 1 and 2, to form an ether channel group. So I'm going to specify interface range, prompt changes to concrete-if. Then I'll say channel group 1. That's an arbitrary number, but it has to match on both of them. Mode active. Well, if I were doing, I would say mode on. I don't want lag P. I want to control the whole show myself. And then it would create the port channel, and then you would type a new command, interface port channel 1. Oh, that's a new name we could put in there. And then we could make it a trunking mode, trunking instead of access mode, and whatever our allowed VLANs are. They got to match on both ends, and it would form a group with the other. Once I go to the switch 2 and do the same thing, they would form the ether channel group with the other one. Now let's do some show commands. I can type show interfaces port channel and see what's going on with the interfaces that have been bonded together and formed an ether channel group. I can do show ether channel summary and see a quick little summary, one line of information per port channel. I can do show ether channel port channel 1, port channel 2, whichever ones I've created, and zoom in on one particular group that I've created. And I can show interfaces ether channel and show FA01, FA02, whichever wires are connected together. It would show me information about those that have been created to the ether channel. Okay, so issues, common issues. They all have to be the same configuration of speed, duplex mode. I can't mix fast and gigabit Ethernet. Can't mix copper and fiber. The native VLAN must match. The allowed VLANs must match. Access VLANs on access ports must match. So assigned ports in ether channel are not, if they're not part of the same VLAN, they're not going to work. If they're not configured as trunks, they should be configured as trunks between different switches. If I try to connect two ether channel groups together and they have different native VLANs, they won't form up. If trunking was configured on some of the ports but not all of them, that could create a problem. It's recommended that when you create the port channel group, don't do any individual configuration. Let's say we're using FA0 /1 and /2. Don't do any individual configuration on 1 and 2 separately. Form a group and then say interface port channel 1 and do all the configuration of trunking on that one. If the allowed range of VLANs is not the same, not going to work. Doesn't matter what you type, it ain't going to work. Okay, so here we have something where port 1 to port 1 of each switch, port 2 to port 2 of each switch, and the ether channel is not working properly. What the heck is going on here? Show ether channel shows us that, ooh, it's down. The ether channel's down. It's not working properly. Oh dear. Show port channel configuration. Oh, incompatible port aggregation protocol modes have been configured on S1 and S2. Got to match, it won't form up. So to correct the issue, we're going to change the port aggregation protocol on to desirable so they can go up. It was auto and auto, they won't go up. Ether channel, he says ether channel and spanning tree protocol have to interoperate with each other. So this is why he did this in the order that it did, in order to, you may see some spanning tree protocol errors as you do the lab. So now, before these were D, D, down, down. Now they're P. They're bundled together. They're working okay. They fixed the problem. Okay. So, hang loose 1 second. I'm going to not share this. Now let me look at the chat. Okay, a question is from somebody that says, I found a 2960 switch so I can practice the commands physically. The 2960 node has iOS version, I think you mean iOS version 12 instead of iOS version 15. So yeah, the workaround to bring it up to iOS version 15, if it's a new enough switch, you should be able to put iOS 15 on it. If you want to bring it in to the lab, we can do that as an exercise for all the other students see in the lab. You generally do have to do a TFTP copy to copy that between them. The file versions that come with the switches, generally you need a support contract with Cisco to do that. However, we are Cisco Networking Academy, and if it's one of the versions of the 2960 switches that is supported with the Academy, if you bring it into the lab, I can quite legally put in an iOS version on that for you. Okay, I'm going to hang loose for a second. But let me stop recording. First of all, stop recording. Please allow me to stop recording.